In this lecture, we start the first fundamental theorem. So, first fundamental theorem. First fundamental theorem. The theorem states that prove that, or we can write down as homomorphic image, every homomorphic image of a group G is isomorphic to some quotient group, of G. So we will prove this theorem. So now every homomorphic image of a group G is isomorphic to some quotient group. So we know about the what is homomorphism, then the image of homomorphism, then isomorphism, and quotient group. So we remember all these definitions. So now we shall prove this theorem. So let G be any group, and we take G dash be its homomorphic image, be its homomorphic image. So there exists a homomorphism F of G onto G dash because it having the homomorphic image. So means that function will be onto such that F of defined from G to G function F onto and homomorphism. So function F is defined as from G to G, which is onto and homomorphism. So let K be the kernel, of F. So then K is a normal subgroup. K is a normal subgroup of G. So we shall prove that. We write down to prove that G over K is isomorphic to G dash. Now we defined this as if X be the element of G because G is a group. So then we take Kx be the element of G over K, and Fx which belongs to G dash. So we define a function phi from G over K to G dash such that phi of Kx is equal to Fx. So for every x belongs to G. So this is our equation number 2. So we define the function phi from G by K to G dash. So such that phi of Kx equal to Fx. So because Fx is the belongs to G dash. Now अब इसको प्रूव करना होगा कि फंक्शन वी हैव डिफाइंड फाई ऑफ के एक्स इक्वल टू एफ एक्स विच इज वेल डिफाइंड और नॉट. So for proving this, the first we show that the function is well defined. So we have to prove that function is well defined. So now to show that function phi is well defined. Phi is well defined. So when we show that function is well defined, so we assume that let x and y, two element which belongs to G, and kx kx is equal to ky. So kx equal to ky. So this kx equal to ky. So when we write down this thing, so we take two element. That means here we take as kx. Kx will belong to G over k. So x and y be two elements. So kx equal to ky. So when we have HA is equal to HB. So it implies that AB inverse belongs to H. So H, so this can be written as when kx equal to ky. So this can be written as xy inverse belongs to k. So xy inverse belongs to k. So which we can write down as function of xy inverse. Function of xy inverse. This is equal to e dash. So by using the definition of kernel of homomorphism. F of xy inverse is equal to e dash. So f of xy inverse equal to e dash. So this can be written as fx into fy inverse by definition of homomorphism. This equal to e dash. Now this can be written as fx into the fy inverse can be written as fy to the whole inverse. So this equal to e dash. So this is also a theorem. So Fy inverse equal to Fy to the whole inverse. Now, this implies that we can write down as Fx into Fy inverse into Fy. So we post multiply by Fy in this equation. So we see that. So Fy to the whole inverse into Fy gives us identity. So Fx into identity E of a function identity you can take as e dash, so which equal to e dash into fy. So fx into identity gives fx, or e dash into fy gives us fy. So fx equal to fy. So this fx equal to fy. So fx, so what is fx here? So fx we defined as phi of kx. So this we can define that phi of kx. Phi of kx equal to phi of ky. So we can write down as by definition. So phi of kx equal to phi of ky. So we can say that function phi is well defined. Function phi is well defined. So function phi is well defined. Now we shall prove that function phi is a homomorphism. So again, to prove phi is homomorphism. Phi is homomorphism. So for proving phi is homomorphism, so proving we take two elements, that means kx into ky. Kx into ky is equal to. So this can be written as phi of kx into ky can be written as k of xy. K of xy. So this equal to function of k of xy. So function of k of xy, that can be written by the definition function of kxy fxy. So this can be written as fxy. So this can be written as fxy. So this can be written as fxy. So here we can write down as f of xy. So this fxy, so by definition of homomorphism, we can write down as f of x into f of y. So f of x into f of y, because f is homomorphism, so f is homomorphism. Now we are proving phi is homomorphism. The function is already homomorphism, you remember. Okay, so this can be written as f of x. So f of x, we can write down as f of x. So f of x is equal to phi of kx. So f of x equal to phi of kx. So this can be written as phi of kx into phi of ky. So phi of kx into phi of ky. So we can write down by using equation number 2. So phi of kx into ky equal to phi of kx into phi of ky. So it means that function is homomorphism. So phi is homomorphism. So here we are proving function phi. Okay. So phi is homomorphism. So when phi is homomorphism, now we shall prove that phi is 1, 1. So now to prove phi is 1, 1. So when we prove phi is 1, 1, so for proving phi is 1, 1, so we take as we have phi of kx is equal to phi of ky. So phi of kx equal to phi of ky. So this can be written as fx equal to fy. So fx equal to fy. So this we write down by the definition. So we can write down as fx into fy. Fx into fy to the whole inverse is equal to fy into fy to the whole inverse. So here we do the post multiply by fy to the whole inverse both sides. So this can be written as fx into fy inverse. So fx into fy inverse this equal to e dash. So this can be written as xy inverse equal to e dash. So we can say that this xy inverse which belongs to kernel k. So K is a kernel. K is a kernel. और K is a kernel. जब x y belongs to G, so we have a subgroup definition. AB inverse belongs to H, so which implies that implied that HA equal to HB. So this you can write down as KX is equal to KY. So KX equal to KY, it means that function phi is 1, 1. So function phi is 1, 1. So we write down as function phi is 1, 1. So phi is 1, 1. Phi is 1, 1. So phi is 1, 1. Now we shall prove that phi is on 2. So phi is on 2. So then we can say that phi is a onto function. So for proving this, so we take y be an element which belongs to G dash. So then f is onto G dash. So f is onto G dash. So there exists an element we take as x which belongs to G such that so which have the preimage such that f of x equal to y. So f of x equal to y. So since x be the element of G, x belongs to G, so then kx belongs to G over k. So G over k such that we can write down the kx, phi of kx is equal to fx, or fx equal to y. So y the definition of function phi. So f of we can write down by using equation number 2. So here function f is on 2. So f is on 2. So then this so that the phi is on to g dash. So g on gy and to g dash. So phi is on to you can write down g over n to g dash. So hence phi is well defined, phi is homomorphism, phi is 1, 1 and phi is on 2. So then G over K is an isomorphism to G dash.